And our first speaker this afternoon is Professor Wladimir Neves from the Federal University of Rio de Janeiro. And today, Wladimir is going to talk about some results related to non-local diffusion equations.
Thank you, Philippe. And first of all, thank you, the organizers, to this really kind invitation. And it's really a pleasure to be here. It's a very nice, congress. So thank you so much. So the outline of my talk will be, first of all, we're going to talk about the motivation, why non-local operations are important. So to convince you that non-local operation, in particular the fractional operation, is important, we are going to talk about two ideas where they come up. One of them is to perturb the cinematics from some stochastic perturbation, okay? And then we'll pass from Stratonovich formulation to Ita formulation, you gain a half of Laplacian. If you use the Brownian motion, you get a half of fractional Laplacian if you use a Levy process. Then we pass to some nonlinear fractional diffusion models. And then we are going to discuss a little bit the initial boundary value problem for a fractional degenerate heat equation. We call it like this. And then you have some final comments. So the motivation, why you should study non-local operators? So first of all, you are related, for instance, to turbulence because of anomalous diffusions. So a very important context where the fractional Laplacian operator comes up is anomalous diffusion, okay? For instance, turbulence is known experimentally and also numerically to have anomalous diffusion, and the application of Levy process to describe it leads to partial differential equations models involving fractional Laplacian. So it's the first idea. I will show you three main ideas, okay? The second idea is this non-simple materials. What do you call about non-simple materials? One recalls that most of the classical partial differential equations describe some physical phenomena related to simple materials, a concept due to Walter Noll in the context of Clifford-Truesdell. This type of materials may have a perfect temporal memory, but only a very limited local effect. For instance, mixtures and porous medium cannot be molded accurately under this assumption of simple materials. Therefore, it seems clear to us that fractional Laplacian operator, in fact, its inverse, can be used to take into account the presence of long-range interactions in non-simple materials. So it's the second idea. And the third one, I said correct regularity. What we mean by this, it's well known that any kind of real process modeled by continuum mechanics must have dissipation. Also, they could have or even develop jumps in many applications. So in this way, the Laplacian operator is not allowed to be present. So somehow you have Euler equations without viscosity, dissipation, or Navier-Stokes equations with the Laplacian. So here you are allowed to have shocks, jumps, but you will not have any kind of dissipation. And in particular, to Navier-Stokes equation, we are not allowed to have some kind of jumps. On the other hand, the fractional Laplacian accepts the existence of shocks and also give you an amount of dissipation. Consequently, partial differential equations driven by fractional Laplacian could give the correct regularity of solution in a large class of real applications. Okay? So I'm going to talk about what we mean by stochastic partial differential equations. So the first idea of anomalous diffusion. And I'm going to give you the difference between what we call intrinsic stochastic PG from forced stochastic PG, okay? So following Inman E, we address some important stochastic forces and PGs in hydrodynamics to study turbulence. So you have here the stochastic incompressible Navier-Stokes equation. So V is the velocity. So this is linear momentum equation. V is the velocity. P looks like pressure, but it's the function of T and X. So nu is the kinematic viscosity. So you have your incompressibility condition, the divergence of V is 0. Just F is a stochastic force. So this is somehow, you are just a forcing term, stochastic forcing term, okay? As observed by E, we could not view turbulence as isolated problem, so now another type of stochastic force equation, it's usual the Burg's equation, okay? So here is, in fact, the viscous Burg's equation. Here, U is scalar, and the other one, V is a vector field, okay? Just to recall more recent application of stochastic force equations, there is this nice paper for Yin Chen, Ding, Kenneth Carlsen. Again, they consider scalar conservation law or system of conservation law. It's just the first term is a stochastic term. Okay? What I'd like to address in this paper that, like us, they are interested in the effect of the noise on discontinuous waves, since these are often the relevant ones, because there are somehow amounts of work, in particular initiated for Franco Flanders, putting a stochastic term inside the transport equation, but to get regularity. It's not the case for us because we are going to start with initial data which is just measured and bounded. So now let us turn to our approach, that is to say a stochastic intrinsic PD. So where comes from this motivation to introduce in this way? So our one side is based on rational continuous physics. So you consider some quantity psi, physical quantity psi, okay? And the supply of psi and the flux of psi. And then the general stochastic balance equation has these four. So instead of the velocity here, you have perturbed the velocity by a stochastic process. So this is the OD, so this is the equation of your characteristic, giving the velocity perturbed by the stochastic term. So Vt is a stochastic process which does not depend on x. Could not depend on x because we are just perturbing the cinematics. You do not want that your deformation tensor or rate of deformation tensors could be changed because of the stochastic term. Okay? So in particular, taking the quantity psi, the density in psi, the linear momentum, we end up what we call a incompressible non-homogeneous stochastic Navier-Stokes equation. So we have the continuity equation, your usual incompressibility condition, and your linear momentum. So here you are not talking about reinforcement, stochastic force term. This is just really intrinsic perturbation of the velocity of your deformation in space, the cinematics. Okay? So we are going to consider in particular the continuity equation or the transport equation since the version of B is 0. Okay? To introduce this, why we are interested in transport equation or stochastic transport equation, I am going to talk you difference between the Muscat problem and what you said, called the stochastic Muscat problem. So just recall you a few lines what we mean by a stochastic problem, or a Muscat problem. So besides the turbulence problem, we are also very interested in the Muscat problem. Hogely speaking, Muscat problem is a piston-like displacement of two immiscible fluids in a porous media domain. We shall assume that there exist two different immiscible fluids in a domain U, bounded, which are separated by an unknown free surface S. Okay? So the mystery density, ρ, is given by this equation. So I put here little w related to water and little o related to oil, just to think like water pushing away the oil, okay? Moreover, the velocity vector field is given by this equation. Then we consider the balance of mass, also called continuous equation in fluid dynamics literature. So this equation should be understood in the sense of distributions. Okay? From the continuity of the normal velocity of the fluids and the assumption of the fluids are incompressible, you have the constraint of the velocity vector fields. Finally, the conservation of linear momentum follows from the C law empirical equation that gives you an equation for the velocity in terms of the minus gradient of the pressure. Okay? These are a constant, could be regular, that's dependent on ρ, the density, in the cinematic viscosity mu. And look like the density, the cinematic viscosity should satisfy the transport equation or continuity equation, if you think like this. So then we formulate the Muscat problem. So let capital T be any real number, okay, and you are a domain in RT, open bounded. So you try to search for whole mu in V solution of this system. I mean, this problem it's open till now. Why? Because somehow to use a fixed point argument, like a Schauder fixed point argument, you have to have uniqueness of the transport equation. And from this equation, you could think that you have just L2 regularity. So it's not allowed to work with the transport equation with just L2 regularity of the velocity vector fields, okay? So instead of this problem, I would like to perturb the transport equation with a very small parameter and introduce the stochastic Muscat problem. So this one. So we consider sigma a stochastic, small parameter, and now the transport equation has this perturbation. Okay, I am perturbed with a Brownian motion. It's not like a Levy process, but it's the inference of the theory, okay? So you have the transport equation for the density, the kinematic viscosity, and what is very interesting here, because we are not changing the type of the equation. So with this type of perturbation, we continue to be a hyperbolic problem. And you have not changed the equation for the velocity vector fields. So you have exactly a sharp interface between the oil and the water, for instance, okay? To try to resolve this problem, first of all, we have to have uniqueness for the transport equation. So then you have a work on it, and we consider the stochastic transport equations for L2 lock vector fields, okay? So the main issue is to prove uniqueness. It's so easy, just have to regularize initial data in your drift vector field, okay? What I mean, the intrinsically stochastic result, because with the L2 lock regularity for your drift vector field, it's not allowed to have uniqueness. There is this nice example from Eisenman, trying to resolve the conjecture of Nelson. In fact, for us, it's clear that they not have resolved it because they consider a vector field in L infinity, but does not have compact support. But certainly in L2 lock, it's not possible to have uniqueness for this transport equation in the determinist case, okay? The uniqueness property relies on properties of the stochastic exponentials. This is the first time we use this type of text function to show uniqueness. And in fact, we are going to consider what we mean are quasi-regular weak solutions. I'm going to show you the definition of it. So as usual, we are considering somehow a linear growth condition for the vector field B because you are in RD. So as usual, your divergence of B is in L1 in time, L infinity in space, but the regularity for B is just L2 lock. We are considered that your initial data is L2 in L infinity, and conveniently introduce the following set of random variables, carried space of stochastic exponentials. So in fact, for each h, little h, you have one f. This is a one-to-one relation from capital F and H. So what do we mean by a solution to the transport equation, stochastic transport equation? So a process in this class is called a quasi-regular weak solution if this integral has a continuum modification and satisfies this identity for each text function phi, which depends just on x, because now you are going to choose a continuous modification of your density, for instance. What would you like to address here? Here, there is a little circle, which means that we are using the Stratinovich integration. It's more physical, correct one to use it. And this is very important because when you pass from Stratinovich formulation to it formulation, it's somehow reading half of Laplacian. So this is the way you could get more regularity or could get uniqueness. Moreover, this expected value, capital V, the expected value of your U times F, has this regularity. It should satisfy this parabolic equation in the weak sense. Okay? So you have our first theorem from N Friedzi and Christian Oliveira. And Euclides was a student from Franco Flanders in Pisa. Now he is a postdoc in Lyon 1. And Christian Oliveira nowadays has a permanent position at the University of Campinas. So under the conditions of hypothesis 1, there exists a quasi-regular solution, weak solution of U to the Cauchy problem 6. So this is already put in the archive. You could see how it works, the proof. The proof of existence is not so new. Now we shall present the uniqueness theorem. The proof of uniqueness of quasi-regular weak solution relies on sub-level regularity of the expected value V. So we have our uniqueness theorem. So if U and V are in this class, are two quasi-weak solutions, quasi-regular weak solutions with the same initial data, then they are equal almost everywhere. The proof is essentially based on energy type estimates on V, the expected value of U capital F. However, to do this rigorous, we are going to use somehow a commutator given by Claude Libri and Pierre Lilions, which has less regularity in F, but more regularity in G, okay? So you use this commutator to show the uniqueness for V, and then you pass for U because of this nice exponential class. So now we turn to what we would like more to talk about, which is the basic fractional evolution model. So the simplest idea to consider fractional evolution equation is this way, which is to say, replacing Laplacians by fractional Laplacians. The former obtains a fractional Heat equation, okay? Albeit, if you want to consider initial boundary value problems, the more realistic ones, this non-divergence form is not good to give the standard notion of weak solution. Since our initial data does not have regularity, I'm not thinking to resolve this like a semi-group theory, okay? I would like to use somehow the weak formulation. So again, this is why I take some time from your attention to consider the Puris-Merge equation. You consider again the formulation of Muscat problem, but now no more incompressible conditions. So P, in fact, is a function of the density. So it's isentropic, should depend also in the isotropy, but just on the pressure. For the density, the pressure depends just on the density. Now it's really a pressure. So there is a really nice paper from Luis Caffarelli and Luis Vasquez. They propose the relation for the pressure of the form P of rho given by this capital rho, where kappa is the inverse of the fractional Laplacian. Okay? In fact, they consider this equation, and under some conditions, they show existence of solution for the Cauchy problem. Hence, the fractional Laplacian operator can be defined using the Fourier transform in this way, well known, which means that the fractional Laplacian is a pseudo-differential operator with this symbol. Okay? Moreover, the fractional Laplacian in Rn could be given by this principal value of this equation, singular integral. And its inverse, that is to say, the Laplacian minus S, is given by convolution with the His kernel. So I'm following the notation from Caffarelli and Vasquez. But what about bounded domains? Okay. Our ansatz, again, is based on rational continuum physics. So then, from different contexts of Caffarelli and Vasquez, we call the ideas of non-simple materials. We propose a non-local Fourier law. That is, the flux of the heat flux, should be given by this function, this tensor, times the gradient of kappa u. So we use the usual temperature, which is heat flux, denotes a non-negative definite thermodynamic tensor. So in particular, for K of x, you have the non-isotropic, non-local heat equation, now posed in bounded domains. That is to say, this is the more correct way for us to look at the heat equation for fractional Laplacian. Okay. Taking the simple isotropic degenerate case of K of x of u go u, we consider the initial boundary value problem. Okay, so this is the problem we are going to be focused, where capital omega t is given by this product. Omega is its open bounded domain having smooth boundary. Okay, And you are going to consider that the initial data is a measure of bounded functions, non-negative, almost everywhere. So you look for U that satisfies this equation, and they are going to give you the exact definition of what do you mean by that. So we are interested in fractional powers of strict positive self-adjoint operators defining a domain which is dense in a separable Hilbert space. Clear here, we are going to consider the operator Laplacian, which has compact inverse. What would you like to say? Like the Laplacian bounded domains, you have many Laplacian bounded domains, which means that what kind of boundary condition you are considering, you have so many fractional Laplacians because of the domains, the condition you are considering the boundary condition you are considering. So due to well-known spectral tree for the Laplacian in a bounded domain omega with homogeneous dictionary data, there exists a complete orthonormal base in L2, blah, blah, blah. This is well known. I will pass through away. So the domain of the Laplacian given by this expression, and the usual Laplacian given by this series. Yeah? Applying the functional calculus for each s from 0 to 1, we are allowed to define the fractional Laplacian in this way, and the domain of the fractional Laplacian is given by this expression. Okay? So then we have the following proposition. This proposition are going to give you the machinery to work with the fractional Laplacian in bounded domains. So just for convenience, call, let's say, capital A, the usual Laplacian. Then the domain of the Laplacian is contained in the domain of the fractional Laplacian for each s, which means that the domain of fractional Laplacian is dense in L2. For each u, the fractional Laplacian is coercive, and the constant of coercivity is just the constant of the Laplacian of the power s. Moreover, the inverse of the fractional Laplacian is just r minus s, and this is a continuous operator. Both the Laplacian and the inverse, Laplacian minus s, are self-adjoint, and so on. So from the above properties, we are allowed to consider the basic estimates. What are the basic estimates? It somehow looks like exactly the basic estimates given by Professor Caffarelli in the Rn case. So the basic estimates gives you, for each s, we are using the same notation for the paper from Caffarelli-Vasquez. So we call that k is the inverse of the Laplacian. In h, will be k.5. So this is a positive operator. So you have a conservation of mass. You have your first estimate. You have your second energy estimate. And you have a maximum principle that gives you the idea of the u is non-negative and should be less than the infinite normal of the initial data. Okay? But how you could consider the solution of this initial boundary value problem? So this is exactly the next definition. Tell us in which sense U of tx is a solution of the initial boundary problem 12. So a measurable and bounded function u in L2 in time, h1 minus s in omega, for any s from 0 to 1, is carried a weak solution of the initial boundary value problem when U of tx satisfies the heat type equation. So this identity should be satisfied for any text function that does not see the boundary, does not see the initial data. So the initial condition should be satisfied in this sense. So since U is bounded, this somehow it's an initial condition turned in the weak sense. Moreover, this is the more important one. The boundary condition should be understood in this sense. So the essential limit as tau goes to 0, the integral in the boundary of this product should be 0. Okay? Where nu is the unitary normal vector field to the boundary gamma. Let's talk a little bit more about this boundary condition. On remarks that, given you in this class, the limit in the left-hand side of 17, the boundary condition I showed you before, does not necessarily exist, since the grad kappa of U has this regularity. and the existence of the trace for U and the grade kappa of U are mutually exclusive. So you already know that to have trace, you have to have S bigger than half. So when U has trace, this does not have trace, and vice versa. Okay? Although for any S, if U is this class and satisfies 15, let's recall. So, in fact, 14, sorry. Then the boundary condition given by 17 makes sense. This is exactly what you have done by this lemma with Gerardo Uraoto. It's my PhD student. He's doing he's a graduate student at Federal University. So if U is this class, for each time T for almost T in H minus 1S, and grade kappa of U in this class for each S, and also you assume that this identity is satisfied for any text function in this class, then there exists a set E containing R plus, a set of full measure, such that this limit exists. Okay? So for any S from 0 to 1. Okay. Next, we consider a more convenient way to express the concept of weak solution to our initial boundary value problem 12. What would you like to say? As I showed you before, the definition had three terms: the identity to show solution of the equation, the initial data, and the boundary condition. So with this equivalence theorem, we already know that the function U is a weak solution of the initial boundary value problem if and only if satisfies this identity. Now, observe that your text function considers the initial data and also the boundary. So what this theorem means, we could pass from this formulation to the three other ones, and then from the three other ones to this formulation. Just consider specific test functions. Okay? And in fact, we are going to work exactly with this relation. Okay? So, with the idea, with the help of the basic estimates, making regularized almost exactly like Professor Caffarelli have done for Rn case, we get a perturbed problem, and these type of snapes are strong enough or stable enough to pass to the limit and show finally the solvability of the initial boundary problem given by the main theorem. So under the above assumption, there exists a weak solution of the initial boundary value problem. Considering uniqueness, it's completely open. Okay? Just to remind you, because you have somehow talked about two different directions concerning how fractional Laplacian appears. So the first one, we are talking about the cinematics. So somehow you are perturbing the flow by a stochastic process. Certainly should be a Levy process, but we have just used the Brownian motion. And here, from your pass from Stratonic formulation to ET formulation, we get the half of Laplacian or half of a fractional Laplacian. The other idea, you are perturbing, or not perturbing, you are considering more general constitutive relations which are non-local. So in particular, for the heat flux, so the Fourier law, we are considering exactly this type of operator, in fact, is introduced by Professor Caffarelli. And then you have we could work with this more general heat equation. So just one more minute, just to say thank you so much for your attention.